Hello friends. So in this lecture, we'll discuss the previous question, what we were discussing in the previous lecture. The concept we have to extend for the t less than very less than the RC and t equal to RC. Actually, these two cases were given as the homework for the same circuit, but I'm covering here. I'm expecting that you people had done the homework and you have to match your answer. Okay, and after that, these two cases are done. We have to modify the circuit so that this circuit can have the same analysis whatever we have done in some previous class. Okay, so we'll see it one by one. Let's consider first the case 2, I should call t much less than RC. What I mean to say, I'm not giving the time to charge my capacitor. Okay, this called T by 2. I can also say T by 2 is much less than RC. Okay, so when we are applying the excitation, so if I consider for T0 positive, what is happening there? You are applying the 5 ampere current, but what is happening? Actually, we are not giving much time to charge my cap. Okay, so the cap is sorted here, V out. So initially I can say IC 0 positive is 5 amp, no doubt. The complete input current is passing to my capacitor that we have seen. Okay, so here what is there? What we speak of IR? IR 0 positive is nothing but 0 amp. Okay, so all current is passing through the capacitor and this current is charging my capacitor. So as we are not giving much time to charge my capacitor because RC is much greater than this value of T by 2. Okay, so simply mean to say, previous class I told that this tau, the RC is nothing but tau, and we have seen from the calculation of tau, which is nothing but comes as R equivalent times the C, or R equivalent comes for this circuit when my current source is open because it is an independent source, it comes to be RC. Okay, so this thing we have seen in the previous class. Now, so if my RC is much greater than the T by 2, it means I applied my current source at t equal to 0 positive, but I am not giving much time to charge the capacitor, and even in a very short time, which is t by 2 in comparison of RC, we are removing the current source. Okay, so let's say my cap is reached to, so VC at t by 2 is reached to some value I call 1 volt. Simple. Okay, so what is happening after the instant t by 2? Okay, it is the same value. So okay, it is nothing but 1 volt. But what is happening with the circuit? The circuit for t equal to t by 2 plus is what? My input is removed or my current source is simply 0, means we are applying or we are making it open. Okay, we are making the side open. But till this point I have seen my capacitor has stored the value which is nothing but 1 volt. And the direction of current which we were considering this way, okay, this is my IR. Here also, this is IC, IR. Okay, so what we speak of IC T by 2 plus. So IC T by 2 plus is nothing but minus 1 upon R. Okay, because 1 volt was stored in the capacitor, and what we speak of IR is nothing but plus 1 by R. Okay, because 1 volt is stored till this time t by 2, and after that we have seen that between t by 2 to t my excitation is not available, so it will discharge also. Okay, so it will discharge, but the time constant is also for discharging, which is RC, is much greater than the other t by 2, which is from the t by 2 to t. Okay, so it will discharge to a very less value. So let I call my capacitor discharge to the value of 0.8. What I mean to say, IC, okay, before the IC I should say, we have seen two things here. IR we have seen, VCP. Okay, so what is happening? T between 0 to T by 2, my cap is charged to maximum 1 volt. And what is happening between T by 2 to T, my capacitor is discharged and reaching the final value to, let's say, 0.8 volt. Okay, because discharging time is very large, It is not getting much time to discharge. Okay, so what is happening at actually t equal to t positive? Circuit is again having the current source applied, which is nothing but 5 ampere. Okay, and this is my resistor R, and this is the capacitor, which has already zero point 0.8 volt across it. V out. Okay, because it has reached to 0.8. I think you are following the discussion. So what is the IR? So we are seeing that here the initial condition, which is after T, IR has some value, which is nothing but 0.8 by R. So what is the value of IC? So IC at T positive, what? 5 ampere minus 0.8 by R. This is the value. Okay. Here for the time being, if I consider my R to be 1, then I can say it is nothing but 4.2 ampere. So slowly we are seeing that capacitor current is reducing. Okay, capacitor current is reducing. Previously, what was this? IC 0 positive was 5 amp. IC T positive. After every time cycle, we are seeing that capacitor current is reducing. So maybe IC 2T plus, it has some, let's say, some value like say 4 amp. Okay, so it is overall reducing. It is not linearly reducing. Just I am giving the number so that you can have the idea. So it is reducing this way. Overall, my capacitor is following again the exponential nature, but in every period it is slowly charging and slowly discharging. Okay, overall, we can see that capacitor is still following exponential nature, but it is taking many cycles to reach at a steady state value. Reach at steady state value. And a steady state value, we already know that it is nothing but 5 times R, which is input current times R. Okay, it is taking a lot of cycles. So slowly what is happening in the cycles we can see. Okay, so what is actually happening? Again, same thing will happen, that I should say it as a VC, also called V out. And this is my time, and I should first plot the input current. Okay, so this is my T by 2, T, 3T by 2, 2T, 5T by 2, and so on. Okay, 0. This is my 5 ampere. It is nothing but IN. On that only I want to plot my V out. What I mean to say, I told that from 0 I reached somewhere here. This value I call 1 volt. I will write here only. This is only 1 volt. And after that we have reduced because my excitation is removed to 0.8 volt. Okay, so after that the increase in magnitude is different, because what we have seen here, the initial slope was slope 0 positive was what? The complete current, which is 5 ampere times the C. What the slope here? The slope here slope at T positive, the charging slope I am talking about, the current is different because due to the 0.8, what is the amount? The 5 ampere minus 0.8 by R. This is the current by slope. Okay, so if I'm considering R to be 1 for the time being or for the simplicity, then it is 4.2 by C. So this the interval of time is same from 0 to T by 2 and T to 3T by 2, but my initial slope is different. Simply means the amount on the y-axis will get different in both the cases. Okay, you should follow this point. Here I am getting 1 volt amount, and here I should get little less amount, that I call it, let's say, 0.8 volt. It simply means this node is reaching to 0.8 plus 0.8 means 1.6. Okay, I think you are following the discussion. And after that again we'll see that here the discharging slope, and in this region I should separately mention slope in the region where I should say t equal to t by 2 plus is what? What is the amount already stored at the capacitor is 1 volt. So what is the current actually? Current is nothing but minus 1 by R for the capacitor. So the slope will be minus 1 by R C. If I consider R to be 1, that is minus 1 by C. This is the slope at T. And what is the slope between? Okay, so the important slope you can understand from here. The slope at 3 by T by 2 plus. What is this? It is nothing but what is the amount of voltage the capacitor has is what is 1 by 6. So current is minus 1 by 6 R by C is nothing but if I consider R to be 1, this is my slope. So here the slope is increasing. Okay. So what we can see, the slope is increasing. Obviously, the interval is same. The magnitude here we are getting, the magnitude here we will get being higher. So let's say it is discharged to some sort of like zero point 0.4. So it is reaching to 1.2 volt. I mean to say this difference is from 1 to pointed means is a 0.2 difference. So I'm just considering this is the difference more than that. Which is 1.6 to 1.2 means a gap of zero point 0.4 here. Okay. Where for the same interval of the time, this gap is minus zero point 0.2. So this gap is minus zero point 0.4. Just numbers I am considering because my time axis has the same window like from this, but the slope is higher here. Let this call slope 1 here and here the slope 2 that I call. Okay, and if I consider slope 1 is greater than the slope 2, okay, in these two time intervals, then the y-axis will be more. Okay, so if I call del y value increment in here and this interval also del y 2, let I call del y 1. So what will happen there? Del y 1 is greater than del y 2 because these intervals are same, del t's are same. Okay, so del t 1, del t 2, when my time intervals are same but slope 1 is greater than slope 2, then obviously the y-axis will reach some higher value in that same interval. Okay, so this is the concept that I want to tell you here. Now you can see slowly it will reach to the final value, which is the 5 volt, or because I can say 5 R because input times R. So the steady state value the capacitor will reach steady state value of VC or V out is what? 5, which is input current times R. Okay. If my R is 1, if I consider, then this is 5 volt. So this thing you have to see. What is the discussion telling here? So if you want to tell, if you want to know about the capacitor voltage, and this thing is simple. Sorry, capacitor current. What is happening? Let I should plot my the input current first. Okay, so this is my 5 ampere. This is my input current, and I want to plot for capacitor current also. So initially, what is happening? Initially, let my capacitor current is means what a complete input. So it is 5 amp. So after that, it is reducing, but to some extent. Okay, let I call to this capacitor current to as capacitor voltage reach to 1 volt. So what is the capacitor current? It is nothing but actually what is the capacitor current at T by 2? At T by 2, capacitor current at T by 2 minus was what? Okay, so let's say capacitor is reached to what I mean to say 1 volt, then it will be what? Means that is a 5 ampere, which is input current, minus this 1 volt divided by resistor. Okay, so let I call this 1 volt to be, if it is charged to 1 volt, then I can say it is charged to 1 volt now. Okay, yeah, 1 volt. So 1 volt, if my I'm considering R to be 1, that is nothing but a 4 ampere. Okay, if I'm considering that R equal to 1 ohm, then this current is reaching to 4 ampere, 5 ampere to 4 ampere. Okay, but at that point of time my excitation is removed So it will reverse its direction. How it will reverse? Okay, so what will be the IC at t by 2 positive? What is happening? Excitation is removed now. If excitation is removed now, this thing is 0. It simply means minus 1 by R. If I am considering R to be 1, let's say, then it should be minus 1 ampere. Okay, so simply means from here it will come to, let I call it, this node is minus 1 ampere. After that it will reach to some higher value, let's say minus 0.8 ampere, and from here it will reverse back to some high value, that is, let's say 4.2 ampere, and after that it will reduce to some value. Okay, so it will reach somewhere here, then after that it will be here, then again here, reach here, and slowly it will reach to 0. Okay, so you can connect these points. Okay, something is happening like this. So slowly we will see that my IC is reaching to 0 in a steady state. Okay, in steady state, IC is simply reaching to 0 means complete I in is equal to IR. Okay, so there is nothing like a sort of a steady state means when we are having a lot of cycles of the input current, my capacitor will reach to its steady state value, and after that there is a no meaning whether you are applying. Okay, IN is this. This is my resistor. This is my capacitor. Okay, if capacitor reaches the maximum value, let's say this is nothing but IN times R, then what is this current? This current is IN. Okay, so complete current is flowing through this. It simply means you can say my capacitor to be open in the steady state. Okay, sorry, it is open in the steady state. Oh, this is the steady state condition. Okay, so I think I could clear my point here. And for t equal to, one more thing, the case t equal to RC again is for homework. I'm not going to solve it again. I think already I have discussed a lot thing. But the one modification that I want to do here is modification in this circuit. If you will do this modification, hopefully you will get the discussion simpler or whatever we have done in the previous classes. So it is what? It is like parallel RC connected with my current source, input current source. What I can do, can I do a source transformation here? Can I apply a source transformation here? If I apply a source transformation here, I can write my structure in the way input voltage and some current, and it is followed by the capacitor. So it is my Vout. Okay. So what is the V in here? When I will do the source transformation, this V in is here is I in times R. Okay, so this circuit is same as the circuit what we were seeing, 1R and 1C from very starting, with the input V in is nothing but I in times R, and we were calculating V out and IC. Here we have seen the extra thing was IR. That thing can also be seen here, IR. Okay, so my circuit is reduced to this value, where we can see what if my in is what, if I'm applying the step of in from 0 to 5 ampere. If this is my I in, then my V in comes to be the step of 0 to 5 R volt. Okay, if I'm applying a pulse of 0 to 5 ampere as my I in, 0 and T naught, then my V in will come to 0 to 5 R voltage. Okay, 0 and T naught. And if I will apply the periodic signal 0 T 5 ampere as my input to this circuit, let I call this circuit 1, this is called circuit 2. This is the side for the circuit 1, this is the side for the circuit 2. Okay, then what we can do, same thing we can do for the circuit 2. Here, what is there? This is my 5 R volt, and this is my 0, this is I in, again this is 0 and T. Okay, so we can simply modify the circuit, simply use the source transformation, and it will be reduced to simple 1 RC circuit, which we have already seen many times. From the very starting, we are discussing this circuit 1R and 1C, and input is applied as whatever the step, pulse, or the periodic signal. Okay, so the value of that will be I in R. Simple, I in R. This is the important thing here we have to discuss. And for this, we have done a lot of discussions. A lot of discussion is done for it. So here, discussion is done for it. So here the point is that, so if you have the idea of single R and C circuit well, then first before going into the calculations, you analyze that can I reduce my circuit to 1 R and 1 C element with the input as a voltage, because we have analyzed this circuit a lot. Okay, so this there is a possibility of reducing the circuit into that fashion. So this circuit with the current source, because no need to deal with the current. Rather, you are dealing with the current. So also a good point. We have seen continued discussion in these two classes, but need not to deal with the current if you can convert into the voltage and the resistor only. So here the source transformation is working for me. Okay. So if no source transformation, if more resistors are there, I can use one series resistor here also, or something else parallel resistor across this I in. Then what if there is a possible try to take the Thevenin equivalent or Norton equivalent. And if you are taking Norton equivalent, you will represent your circuit in this fashion, and that you can convert using the source transformation, or directly you can take Thevenin equivalent. That will be nothing but a one voltage source, one resistor, so that you can apply your capacitor across that, and the rest analysis will be same whatever we have done in the previous classes. Okay, so this is the modification that I want to do in this circuit. Okay, I think I could clear my point, and it is clear to you how to analyze this. Okay, so here we have seen with the time very less than the RC, and what the discussion is, I think a thorough discussion has happened here, and you go through the video again, and what modification I have done, you see it once more. Okay, so I think I could clear my points. The only case again I left there is T equal to RC is not a much complicated here, so you can analyze this. Okay, I think in the one previous question also I left this case T equal to RC, so you should analyze that also, and I'm expecting that before coming to the next class you are solving whatever the problem given for the homework. Okay, so it is enough for this video. We'll see something else in the new video. Thank you.